This week we're going to learn more about redox tables. You started creating tables with the lab you did last week. Now, with redox tables, we need to know a little bit about spontaneity. So when we created our table, we listed the strongest oxidizing agent at the top left of our table, and we wrote reduction half reactions for the table. And that is how you will use the table. If your oxidizing agent is above your reducing agent, that means you're going to produce a spontaneous reaction. If your oxidizing agent is below your reducing agent, the reaction will be non-spontaneous. Now, in the Alberta curriculum, the reduction half reaction table lists the strongest oxidizing agent at the top, but in your IB data table, you will see that the strongest oxidizing agent is at the bottom and the strongest reducing agent is at the top. Now let's look at how we can create an activity series or a table using some given lab data. And in order to do this, we need to remember a little bit from our previous lessons. When we have a gain of electrons, it's reduction, and that would be an oxidizing agent if the substance is gaining electrons. And when we have a loss of electrons, it's oxidation, but that would be a reducing agent. So we know that oxidizing agents become more negative because they gain electrons, whereas reducing agents become more positive because they're losing electrons. So now with our table or our data set that we have here, we see some different reactions. When we see no reaction, or if we see an arrow and above the arrow it says non-spontaneous or non-spawn, we know that that reaction doesn't occur. With each of these reactions, we need to identify the oxidizing agents and reducing agents. So remember, oxidizing agents will become more negative. So if a positive ion becomes neutral, that would be becoming more negative. So this would be my oxidizing agent, and therefore my A must be my reducing agent. And because I'm always working with positive ions in this, it's really easy to go through now and list all the positive ions as my oxidizing agents and all my neutral atoms as my reducing agents. This isn't always the case, but in this example it is. Now remember, in our Alberta curriculum, which is what we're focusing on, we have the oxidizing agent on top and the reducing agent on the bottom producing a spontaneous reaction. So with that, we need to think, okay, if there is a spontaneous reaction, which means I have the arrow moving and I have new products on the other side and there's no non-spontaneous above the arrow, that means the reaction is happening spontaneously, which means my oxidizing agent, in this case the B+, is going to be above my reducing agent, the A. So I can say that B is over A. And then I look at my next reaction and I have C+, which is reacting with B, but it's a non-spontaneous reaction. So my oxidizing agent must actually be below my reducing agent. So therefore I would say my reducing agent B is above my oxidizing agent C. I then go to my third reaction and I have A and C reacting, and it's a spontaneous reaction. So then I know C is above A. And last but not least, I have a spontaneous reaction between the oxidizing agent D and the reducing agent B. So D must be over B. Now we look and we say, oh, D is over B, but B is over both A and C. So we can automatically know, because there's only 4 different atoms, that D is on the top. D must be first, and B then must be second. Now we just have to figure out which one's better between A and C for oxidizing agents, and C is above A. So then C becomes third, and A comes fourth. And then sometimes we're going to be asked to not just order them in terms of which is the strongest oxidizing agent. We might actually have to write out the reduction half reactions for each of these. And because these are all 1 positive ions as oxidizing agents, it's really easy. We just add the 1+ to each of those. We're going to add 1 electron because we want to neutralize the ion and we are going to have the element on the other side of my reaction. So this would be our reduction half reaction table. Here's one more that you can try. Pause the video, write out the oxidizing and reducing agents, see if you can come up with the right half reaction table. I went ahead and listed the oxidizing and reducing agents. Now we need to get our individual piece of evidence from each reaction. First reaction tells me my oxidizing agent is above my reducing agent. CD is over BE. Second reaction, my oxidizing agent again is above my reducing agent because the reaction is spontaneous. So H is over CD. My third reaction, copper and beryllium, produce a spontaneous reaction, and copper is my oxidizing agent, so copper must be over beryllium. And my last reaction between copper and hydrogen produces no reaction, and so therefore my reducing agent must actually be above my oxidizing agent, so Cu is over H. From the last one, Cu is over H. We also know Cu is over Be. The only one we're not sure about is Cd, and we see that H is over Cd here, so Cu must be at the top. Next, we look and we say, oh, H is over Cd, and Cd is over Be from this reaction, so H must be second. And then finally, Cd must be third, and Be must be fourth. It's kind of like a logic puzzle to figure these reactions out. Now we have to look at each half reaction to complete the table. Copper is a 2+ ion. We must add 2 electrons to it to become copper metal. There are 2 hydrogen ions, plus 2 electrons make H2. Cd2 plus 2 electrons makes Cd, and Be2 plus 2 electrons makes Be. And so there's our half reaction table listing strongest oxidizing agent top left and strongest reducing agent bottom right.